You'll also notice that I actually solved it in a different way than I normally do. Yeah. If you guys are having a problem with the normal way I solve things, I can change that. It's easy. That's just the way I normally solve them is actually the lowest contextual way, meaning that you can actually do it the easiest on exam. Okay? All right, so then that's the answer right there once you put that in the calculator, right? Okay, fantastic. You may actually want to put these things in calculators. When I start problems, that's actually your best way of learning, is to see if you can actually get the answer out, okay? Because you'd be surprised how many times you're like, oh, that's really simple. And then you get home on an exam or you get home on a homework and it's like, oh, I don't know one step. That's not good. Okay, sublimation and deposition. Now we have fusion / melting, right? It goes from a solid to a liquid. We have where it goes from a liquid to a gas, and that's called vaporization, right? Okay. Okay. And then what we have here is what's called sublimation. So sublimation is going to be where you go directly from a solid into the gaseous form. Right? Anybody ever seen dry ice? That does sublimation. So if you've ever seen dry ice, you've seen sublimation. Okay? Does anybody want to argue with me on that one? No, I get that quite a bit. And it's because when you're doing dry ice, what happens around here especially is the water precipitates around it, right? And that's the liquid you're seeing is water, right? The water precipitating around it. So, nope, you've never actually seen liquid CO2 probably. If you have, it would have been very, very high pressure, okay? The particles on the surface of the solid are going to change directly into the gas without going through the middle phase, which would have been liquid normally. There's going to be no change in temperature again because all the energy that's coming into this is going to get used up going to the gas phase, breaking all of those connections, right? In the reverse process, this is actually called deposition. Gas particles are going to change directly into a solid. Anybody ever heard that word, deposition? In this context where it's going to a solid? No? Legal context? Yeah. Yeah. Deposition, when you go in a scientific context, is always this. And yes, that's how they make computer chips. Okay? In case you were wondering. This one, again, is going to be where you're actually losing heat from the system. And so the temperature here is, again, not going to actually, it's not changing temperature causing this. Does that make more sense? No? Okay. Yeah. You're going to be releasing heat from this system. Does that make more sense? You ever been behind your fridge? No? Not even a small one? Like you've never been behind a fridge? Really? No, you walk behind fridges because sometimes they're not right up against the walls. Like you've never been to a store and been behind a fridge because they have it out? No? Wow. Okay. All right. How about an air conditioner? Yeah? Have you been the other side of the air conditioning? I.e. where you've, yes, it's hot, right? Yeah. So it blows cool air out at you. If you go to the other side, which is that big air conditioning part in the backyard, or if you have the small window-mounted ones, the other side of the window, what you'll feel is that it's exchanging heat, right? And it's actually doing that through a compressor, very similar process to this. That's compressing the gas down to a more dense gas or a liquid, okay? And that's actually why it dehumidifies your house. You guys know that, right? No? Okay. Okay. Um, all right. So, think of it like this, is that you're paying into the system, right? You're paying energy into these systems, okay? Or you're extracting energy out of these systems, okay? This one right here, we're actually extracting energy out. That's what minus heat means. It's coming out. This one right here, we're putting energy in, okay? That energy is getting consumed doing these transitions, okay? In this case, the energy is being consumed doing that transition. In this case, the energy is being released by that transition. And it's not being consumed or released due to temperature, okay? Does that make more sense? Okay. Okay. If you have been to the other side of a compressor, that's what those are called. There's one in a fridge, there's one in an air conditioner. Then you've actually experienced a practical application of this. Okay? Okay. So let's talk about evaporation. This is another example of that heat being drawn away, by the way. You know how you sweat? Everybody's experienced sweating? Okay, thank goodness. If this hasn't been experienced, then we have a lot of troubles here. Okay, so when you sweat, what's happening? You're releasing liquid, right? Okay, and what does the liquid do? It cools you down. How? It evaporates. Yeah. So your liquid evaporates, right? And that process of evaporation pulls energy into the liquid, the water droplets. Okay? That's the energy that's actually being used to break them away and form the gas, right? Okay. And so this is again another application of that. And you notice that your temperature changes, but the temperature of the water drops and the surrounding of you doesn't change much, right? Yeah, that stays constant. Okay, so again, evaporation is going to occur when you have sufficient energy to launch these water molecules out of the solution, and they will actually take that extra energy with them. Okay. By the way, is space cold? Is it warm? It's nothing. Yeah, space is nothing. Space, in fact, is a really good insulator. Did you know that? Anybody ever used one of those vacuum doers or vacuum mugs? The really, really, really expensive, like hot water holders or tumblers. You give them for like $100-something. And they last for like all day. I've had one that I came back a day and a half later, and it was still hot. So those ones are actually vacuum tumblers, those really expensive ones, and they have a layer of vacuum between. Yeah. So vacuum is actually a great insulator. Why do things freeze when you throw them out of the space station? Anybody know? This. If they're in vacuum, then all the particles that can release, they're not going to come back, are they? They have nothing to bounce off of and come back. And so you lose a bunch of molecules that you lose all that energy from, because none of them ever come back and run back into you. Yeah. Normally when you're in the atmosphere, anything you lose bounces off the air in the atmosphere and comes back at you. It freezes because you're losing all that energy. Loss of energy causes your temperature to go down. Yeah. Normally you'd be recycling the energy back into you. Yeah.
It's like the sun, not like true but
Yeah, it's just like the sun coming down on the Earth. And the reason we are the current temperature we are on planet Earth is because we recycle a significant amount of that energy back in. Okay, so at the boiling point, molecules are going to have enough energy to overcome their attractive forces. They'll become a gas. That's actually why things boil. That's literally what being at the boiling point means, is the average amount of energy in that system can launch water molecules out into the gas phase. Think of it a bit like little space shuttles, okay? What happens if you don't achieve escape velocity with a space shuttle? Yeah, doesn't escape, does it? Okay? If you don't have enough energy behind these molecules, they are not going to escape, right? Yeah. You have to overcome that. And that's actually what boiling is. In condensation, we're actually going the reverse direction. We're going from a gas back to the liquid. You've actually seen condensation if you ever take like a cold glass or a cold can of something out on a hot day. It always has water that beads around the surface, right? And that's condensation. That's actually causing your drink to become less cold, isn't it? Yeah. Because heat is then escaping those gas, liquid, water exchange. So going from the vapor phase of the water to the liquid phase of the water on the surface of your glass is putting out heat onto it. Okay, so again, what temperature would that happen, by the way? If I have a boiling point, what temperature is that? The temperature something boils, but it's also the temperature at which something would go the reverse. Yeah, because it's just like a doorway, right? Okay. If I'm on this side, I'm in the classroom. If I'm on that side, I'm out of the classroom. What point do I achieve the difference? The doorway, right? Same thing with a melting point. A melting point is the temperature at which you're going to go to the liquid from the solid, but it's also the temperature you're going to go from the solid to the liquid, back from the liquid to the solid. Okay? It is the point where you're at a balance between the two. Okay? All right. Now, heat of vaporization, this is going to be the amount of the heat that's going to be absorbed to change 1 gram of liquid to a gas at the boiling point. This is released when 1 gram of gas changes to liquid at the boiling point. And again, it's both directions. Think of these as a step from one direction to the other, and then you go down the step going backwards, right? So again, they will go either way. If you're going to from a liquid to a gas, you're going to absorb energy. If you're going from a gas to a liquid, you're going to release energy. So for H2O, this is actually 2,060 joules of heat that's going to be used to convert 1 gram of water to steam. This would happen at 100 degrees Celsius. And again, that would be the heat of vaporization, which is the same number going either way. So let's talk about the heat of condensation then. This is what you would call it if you go backwards. So if you go from the water vapor, gas, back to the liquid, it's the exact same number. It just goes the reverse direction, right? And see, those are the same number, 2,260, 2,260. Okay? All right, now, the heat of vaporization again, or condensation of water. This can be used as a conversion factor. And again, these would be the conversion factors. And we can flip those upside down if we need to, right? And that would relate the joules to the grams that you are converting. Again, this would be the calculation right here. That would be the heat equals mass times the heat of vaporization. If you want a formula, that would be the formula. So how many kilojoules are released when 50 grams of steam from a volcano condenses at 100 degrees Celsius? Okay, so again, we have 50 grams, right? Okay. What do we need? Kilojoules, yeah. Question mark. Okay. And we're also going to need one other item, aren't we? And it's not on the slide. We're going from steam, we're condensing it, right? Okay, and so we need to go back one slide, and we need to grab that number. We want the one in joules, right? And so we need this one right here. What do we want to get in? Kilojoules, so we need the one in joules, don't we? Okay. Okay, and so we're going to grab that 2,260 joules per 1 gram. And, okay, what do I do next? So I have grams now. I have something that relates joules and grams. Yeah. I just need to take that 50.0 grams, right? And I need to put that times 2,260 joules per gram. Notice grams will cancel. I take the 50 times 2,260, and that is my answer, isn't it? Am I done yet? No. What's the last step I need to do? Yeah, I need to get in kilojoules. And that's it right there. What's up? Okay. Now, does anybody have any questions? They're really kind of the same question, wasn't it? Yeah. It's just we use a slightly different, because we are condensing this time. Now, what did I really say now? Am I releasing that 113 kilojoules, or am I gaining that 113 kilojoules? I'm releasing it, aren't I? And so if I have steam from a volcano and it's trying to come in contact with me, what do? Nobody knows what you should do if steam is coming off a volcano and shooting at you. Run away. Run. I'm a little worried for you all now. That was a long pause. I feel like that steam would be shooting now. Okay. Now, this is a heating curve. This is actually how I prefer to think of most of these problems. If I'm doing something that's more complicated than just one step, I like to think of all of these problems like a heating curve. Okay? So on a heating curve, we have diagonal lines. These are the diagonal lines right here, right? And that's going to indicate changes in temperature for a physical state. So here we have liquid, and it is heating up. Can everybody see that okay? We put energy into it, it heats up. Cool. And it's going to do that between what temperatures? 0 and 100, exactly. And we can get that off the graph, can't we? Right there and there. Or we could know the melting point and boiling point of water, couldn't we? Because what's going to happen at the melting point or boiling point of water? Yeah, we're going to have phase changes, right? Yeah. We're going to go from one phase to another. And when we're at the melting or boiling point, see how that line's flat there? So what that tells you is the temperature is not increasing at those points, okay? Now I'm going to tell you in the real world, they're not going to be perfectly flat. They'll have a very, very tiny slope, okay? But you'll be able to obviously go, this is a lot more flat than that. Just the real world doesn't exactly work out like our models in our heads, right? Yeah. Okay. And so again, melting is right here. And so you can see in application what we've been talking about in theory, can't you? You can see this is solid water. We're heating it up, okay? We're literally heating ice up. It was lower than 0 degrees Celsius. Now it's going up to 0 degrees Celsius, okay? And then here we pour in energy, but we don't get any temperature change because we're having to break apart all those connections, right? And get into liquid water. And then again, we get a temperature change that's starting to happen because we're heating that liquid water up from 0 up to 100. And then over here, we're pouring in energy to break all those remaining connections so it can go into the gas, right? And then again, we have gas, and we can heat that up. Why don't I have any ends to these? Yeah, they can keep going up and up and up, or down and down and down, until we hit something that causes a much larger interaction, okay? If we go down far enough, we're going to literally get to absolute zero, right? If we go up enough, we're going to start doing things like shooting all the electrons off our atoms. And we'll start getting like nuclear fusion and stuff, okay? We'll get some crazy stuff happening. But for these, for our effects, they essentially just go up and we don't care because you're not going to have to worry about that. This is a cooling curve. What do we notice about the cooling curve? It's the exact same thing. You'll probably never hear me say cooling curve ever again. I know. Just because a heating curve and a cooling curve, they're the exact same thing. They're just flipped. Okay? That's the only difference between them. All right. And so, a plateau, horizontal line on a heating curve represents what? Is it a temperature change? Constant temperature? Change of state? It's a change of state. What else is it? Yeah, it's a constant temperature. It's a change of state. You got it. So a sloped line on a heating curve represents what? Yeah, it can only represent A, can it? Yeah, we're putting in heat. We're also raising the temperature. We don't have any real phase changes happening there. Okay? Okay. So using the cooling curve for water, let's answer each of the following. So water condenses at a temperature of what? Yeah, 0 degrees Celsius. I'm sorry, condenses is 100 degrees Celsius. Yeah. I was thinking about the next problems. So we're going to condense 100 degrees Celsius. Perfect. The temperature of 0 degrees Celsius liquid water is? What's happening there? Yeah, freezing. Anything else? Yeah, exactly. We're going to go both directions, aren't we? Think of it like an ice bath. If I started with liquid water and I put it at 0 degrees Celsius, I threw it in the freezer, I'm going to freeze that, aren't I? But on the other hand, if I started with an ice bath, ice, and I had ice sitting around, it's going to be 0 degrees Celsius and it's going to be warming, isn't it? It's going to be going to liquid water. Okay? So we can approach it either way. At 40 degrees Celsius, water is a what? Liquid. You got it. You got it. When water freezes, heat is what? Which one? Sorry, I actually can't hear you guys over this. This is actually really loud. Hey, fantastic. Thank you. Yeah, by the way, what is that that's making all that noise back over there?
It's the AC.
Is it? Wow. That must be the fan, isn't it?
Get in there and find out.
No, I'm good. All right. So, by the way, that's actually, did you hear that thump sound? That's the condenser that we were just talking about. So, a 175 gram sample of steam at 100 degrees Celsius. This is emitted from a volcano. It condenses, cools, and falls as snow at 0 degrees Celsius. How many kilojoules were released? Ooh, so we have several different steps to this one, don't we? We have, what do we have? I'm going to make you do it. We have 175 grams of steam, right? Okay. We started at 100 degrees Celsius when we emitted from a volcano. We're then going to condense. It's going to fall at snow at 0 degrees Celsius, isn't it? Okay, so we're trying to then figure out how many kilojoules was released through that entire trip. Now, first thing we need to do is we need to actually figure out what that trip was, right? And so I'm going to make a heating curve, okay? Okay, so if we started with the gas at 100 degrees Celsius, right? We started up here, 100 degrees Celsius, didn't we? Okay. And this was the gas. So the first thing we actually have to do here is we have to go from the gas to what? The liquid. Yeah, because we're going to eventually be the solid, aren't we? So the first thing we need to do is we need to go from the gas to the liquid. Okay. And that's going to happen at what temperature? Are we going to have any temperature changes for this? No. It's going to happen on plateau. And so that's our part one of our problem right there. Okay. The next thing we're going to do here is we're going to go ahead and go down in temperature because we need to go down from 100 degrees Celsius down to what? 0, exactly. Okay. Once we're at 0 degrees Celsius, what can we do? We can go from liquid to solid, exactly. Okay. And that's actually the end right there. And so that is our solid. All right. And so we have a second region right here, and we have a third region right there. And so there are going to be 3 parts to this problem. Okay? At the end of this, we want kilojoules. All right. And so the first thing we need to do is we need to somehow use that energy that's released going from vapor or gas to liquid, right? Okay. Which one was that again? There was a number I gave you. Do you guys remember what it was called? Yeah, that heat of vaporization, that was that 2,200 and where is it? 2,260 right there. Okay. Okay. And so we need to look that up and get that 2,260, right? This is just the gathering of all the numbers, by the way. That right there is the heat of vaporization. Okay. So gas going to liquid, right? This right here is the specific heat. This is region 1, region 2, and this one right here is going to be region 3 on our heating curve. Mm-hmm.
So is heat of vaporization any liquid to gas or gas to liquid?
You got it.
Either of them?
Yep, it's that, it's just the number that takes to either form or break those bonds. Yeah. Yeah. And in fact, an interesting side note to this is, you remember your heating and cooling curves, how that vaporization part was a lot longer, and then the condensation, the going to the solid was a lot shorter, okay? That's actually these numbers here, 2,260 versus 334. If you were to measure those out and compare them, you'd get that. Yeah. Okay, so what we're going to do now is we're going to do this in basically 3 steps. We're going to do essentially 3 problems and add them together at the end. Okay? All right, so the first one we do is we're going to calculate the heat released as the steam is condensed from the vapor to the liquid. Okay? And so we had 175 grams of H2O. This is times 2,260 joules per gram. Okay, everybody good with those numbers, where they came from? Fantastic. Now, the last part being that we want to be in kilojoules, don't we? Yeah. And so we can go ahead and do this conversion here in each of these problems, or we could have done it at the very end. It doesn't matter. Okay? I'm going to do it in each of the problems just so it doesn't throw people off as much. Okay? Just a little easier that way. When you actually do this problem, don't round it. I'm keeping track of my sig figs here, But when you're actually doing this problem, don't bother rounding these last numbers right here until the very, very end. Okay? Because you'll get errors that add up then. All right, so the next part we have to do is we have to do the temperature change, don't we? Everybody remember that specific heat problem we did before? Kinda? Maybe? Okay. Okay, and so we're going to take the temperature change. In this case, it's going to be going from 100 to 0, and so we get temperature change of 100, don't we? Yeah. 100 degrees Celsius. Very good. All right, so the next step here is we're going to calculate the heat released as that liquid is cooled. And again, we're going to use that same mass because our mass didn't change. We didn't lose any water. We're going to go temperature change of 100 degrees Celsius. That's that delta T. Okay. This right here is the mass. This here is the specific heat. Okay. Right there. And we're using the one that's joules, grams, over grams, degrees Celsius, right? Okay. Because we want to be in joules, not calories. Okay. Notice, by the way, your units here actually tell you what the formula has to be. Because you're going to have to get rid of grams and degrees Celsius, right? To get into joules. Okay, and finally we're in joules, and so we're going to go to kilojoules. That means taking 1 divided by 1,000. Okay. Okay. All right. So again, 175 times the temperature change times the specific heat times 1 over 1,000. And that gives us our answer, 73.2 kilojoules. Okay. All right, so the next part is, and this is the last part, is we're going to calculate the heat released as we freeze it, right? We're going to go from liquid to ice, which is snow. All right, and so again, we're going to take that mass of the water, 175 grams. This case, we're going to use that the heat of freezing or the heat of fusion, same number. And then that's going to, again, be in joules, and so we need to go into kilojoules. Okay? Okay. And that's going to give us this 58.5 kilojoules. Did I lose anyone anywhere? Okay. Notice it's the same 3 problems we did before. We're just doing them all together. Okay, what's our last number need to be? Well, it's not any of those individual numbers, is it? No, we have to add those 3 numbers up, those 3 regions together, okay? Because our total number is going to be taking that cooling curve and adding it all the way to the bottom, right? Okay, and so we're going to add those numbers up. We have 396 kilojoules plus 73.2 plus 58.5 kilojoules. And so the heat that is needed to do this is going to be 528 kilojoules when we add all those together. Please note that the conversion of the vapor to the liquid is almost always the vast majority of your energy. So if you just do that, it already gives you a pretty good idea of what you're going to get. Okay? And so you add all those up, it's 528 kilojoules. We go back to our A, B, C, D, and that was this number here. Did anybody notice something that I could have saved myself a bunch of time if I was trying to do this like last minute on an exam? So because I have to give you a range of answers that aren't all right next to each other, if you do the first part, if you do the vapor going to liquid, you know it has to be greater than that, don't you? But not massively so. And so if you do that part, you already got the answer. Okay. So if you're like doing this last minute on an exam or something, there you go. Always concentrate on the part where you go the vapor to liquid or liquid to vapor. Okay? Because that will always give you something that's probably half or greater than your energy. Okay? All right. Okay, and that is the chapter. We'll be moving on to chapter 3 now. Did anybody have any last minute questions? Close out chapter 2. Chapter 3, moving on to 4. We're going backwards. Nope, nothing? Okay. Okay, fantastic.